Okay, welcome to Stability in Cloud Development Part 1. This is Chapter 6 for ESCI 211. Okay, so the learning objectives for this part of Chapter 6 are to know the definitions of stable and unstable, the causes of stability, and how to determine stability. So, what is stable or unstable? By definition, a stable equilibrium is if we displace an object, it will return quickly to its original location. In our case, if we move an air parcel, it will resist moving up or moving down and go back to its original location. An unstable equilibrium is an object, if the object is displaced, it will move away from its original location. For us, it will be an air parcel. So if I move the air parcel up, it will keep going up. If I move the air parcel down, it will keep going down. So this is an example of a stable equilibrium right here. So we have an object at the bottom of the hill. Now if I move this object up the hill, okay, and let go, it rolls right back down to its starting location. That's called a stable equilibrium. Here's an example of an unstable equilibrium. If I have an object at the top of the hill and I let it go down the hill, it keeps going down the hill and doesn't come back. That's unstable. All right, so let's define an air parcel. So this definition should help us develop a model for our stability. So an air parcel is the following: about the size of a basketball. It can expand and contract freely. It cannot transfer heat to the surroundings, and it cannot gain heat from the surroundings. So what will happen what will happen to the parcel if it rises? Okay, so here's what I want you to think about. The surrounding air pressure as you go up, the mass of the air in the parcel, and the space between the air molecules in the parcel. So if the air parcel rises, it should expand because there's less pressure. But we still have the same number of, or same mass of the air parcel and the same number of molecules, but in less space, or sorry, not less space, in more space. So there's more space between all the air molecules. This will allow them to move around with having fewer collisions. And so thermodynamically, this is considered cooling the air parcel. So if an air parcel expands, it will cool. Okay, what happens if an air parcel sinks? All right, so the surrounding air pressure increases. The air parcel will be compressed. The parcel still has the same number of mass and number of molecules, but in less space. So we should have more collisions than we had before. Thermodynamically, this means the parcel is warming. All right, so here's an example. Got the surface of the Earth, got an atmospheric pressure at the surface of about 1,000 millibars, got an atmospheric temperature about 20 degrees Celsius. So I got my air parcel on the ground. If I move it up, it will expand and decrease in temperature. It expands because the air pressure is less than on the ground, in this case about 900 millibars. Now, if I have an air parcel that's up at this level and I want to push it down, it will compress and the temperature of the parcel will go up. All right, so this process of expansion being cooling and compression being heating is called an adiabatic process. And we're also assuming that this process exchanges no heat with the surroundings and no heat from the surroundings get transferred into the air parcel. Or we'll refer to it this way: there's no energy change from the parcel into the surroundings, and there's no energy change from the surroundings into the parcel. This is called an adiabatic process. So, in the atmosphere, we will have two types of parcels. We will have an unsaturated air parcel. That's an air parcel whose humidity is less than 100%. And we'll have a saturated air parcel. That's a parcel whose relative humidity is equal to 100%. These two parcels will have different heating and cooling rates. This unsaturated air parcel uses the dry adiabatic rate. It increases or decreases in temperature by 10 degrees Celsius for every 100 meter change in height. The saturated air parcel, which uses the moist adiabatic rate, which means that parcel will heat or cool by 6 degrees Celsius for every 100 meters change in height. And so you see that an unsaturated parcel and a saturated parcel behave differently. Can you figure out what in the saturated parcel could transfer energy to increase the temperature of the air in the parcel? So here's an example of expansion and cooling. So if an air parcel from the surface is lifted up 1,000 meters, it's going to cool 20 degrees. If this air parcel is lifted up another 20 meters, it's going to cool, another 1,000 meters, it's going to cool another 10 degrees. Now, if we do the opposite, we bring this 10 degrees parcel down, it's going to compress and warm by 10 degrees. If we bring this 20 centigrade parcel down, it's going to compress even more and warm by another 10 degrees. This is how at least an unsaturated air parcel warms and cools as it's going up or down in the atmosphere. Alright, so here's how we're going to determine stability. First of all, we're going to have to know what is called a lapse rate. And basically what the lapse rate is the change in temperature as we go up in elevation. So a dry adiabatic lapse rate is a change in 10 degrees Celsius for every 1,000 meters. A moist adiabatic rate is a change in 6 degrees in temperature for every 1,000 meters. So those are two lapse rates that we're going to use. A third one is the environmental lapse rate. This is how the actual temperature in the atmosphere changes as we go up or down in the atmosphere. We also have a lapse rate for dew point. As you go up and down in the atmosphere, the dew point will increase or decrease by 2 degrees Celsius for every 100 meters change in altitude. For every 1,000 meters change in altitude. So, definition of a stable air parcel is an air parcel that's cooler than its surrounding air. Since it's cooler, it is more dense, and if we try to lift it up, it will tend to come back down. The way we determine an unstable air parcel is an air parcel that's warmer than its surrounding air. Since the warm air is less dense, it will tend to keep rising if we lift this air parcel up. So there is also an atmosphere that's called an absolutely stable atmosphere. And this happens when the environmental lapse rate is less than the moist adiabatic rate. So basically, if you try to lift an air parcel up, the air parcel will always be cooler than the surrounding air and want to come back down. So, what do you need to remember from this online lecture? You need to remember the definition of stable and unstable. We're going to use them in part 2. You need to remember the causes of stability. And you need to remember how we determine stability. All right. All you have to do now is watch part 2 and learn more about stability and cloud formation in the atmosphere. I'll see you next time.